equations. Let's just say that one of your equations, in the question it says when you divide by x minus 2, the remainder is 7. That's given in the question. So what you would end up doing is you would have an equation, I'm just going to call it equation 1, where you would say 7 equals, and then you might have 3 times 2 cubed plus 4 times 2 squared minus 8 times 2. Oh, I guess you've got a's and b's in here, don't you? Yeah. So you might have, and this is going to be, decidedly different than yours. But you might have a times 2 squared minus b times 2 plus 10. So you've set up your equation and you're using the remainder theorem. Your explanation doesn't have to say I'm using the remainder theorem, but I believe that what I'm going to put in green is almost necessary for a complete response. I think this is crucial. I think some statement of you saying that the remainder theorem is leading you to this idea that p of 2 is equal to 7. Give me 1 minute, okay? Is there anybody else other than Tamia that needs that assignment? Okay, and I will get it to you. So once again, everybody, that assignment is due tomorrow. That's the official due date. And if you want, you can turn it in Friday. But if you turn it in Friday, you're not going to get it back before your exam on Monday. Okay, so you have to make that decision. Anyway, let's take a look at what we were doing yesterday. I'll hand back your quizzes in a little while today. What we were doing yesterday was dealing with finding equations of graphs, and it had to do with multiplicity. So we learned, see if I can find one here that has both. There's one. We learned that x-intercepts on a graph have particular features to them, and an x-intercept can either go through nice and cleanly, like this x-intercept, or this x-intercept. And what that means is that the factor that produces that x-intercept occurs only once in the factored form of the function. So this function p of x, or f of x I guess it's called, would have to contain an x minus 3, and it would be to the 1. The reason is this x-intercept, I guess it would be x plus 3. This x-intercept is equal to negative 3, which means we need a factor that has a 0 of negative 3. But because the curve goes through that point nice and cleanly, it doesn't wobble, it doesn't waver, it doesn't hesitate, it just goes through with determination, then the degree on that factor is 1. And we call that degree multiplicity. If you take a look at this x-intercept here of 1, it also goes through really cleanly, which means that that also has a multiplicity or a degree of 1. And we've learned that if the x-intercept is 1, the factor is x minus 1. But this particular x-intercept at positive 3, which would yield a factor of x minus 3, doesn't actually pass through the x-axis. It's tangent to the x-axis. So this is a point of tangency, and this is at x equals 3. And we learned yesterday that if the x-intercept occurs at a tangent point, that's a multiplicity on that factor of 2, or a degree of 2. By the way, a few of you have asked me this, and I should answer it for everybody. We would say that the degree or multiplicity on the x plus 3 is 1. We can say that the degree on the x minus 1, or we can say the multiplicity on the x minus 1 is 1. We can say the degree on the x minus 3 or the multiplicity on the x minus 3 is 2. But when you talk about the entire polynomial and you say the polynomial function has a degree of 4, you can't say the multiplicity of the polynomial function is 4. The multiplicity refers to individual factors. And finally, if you have what we call an inflection point, then that has a multiplicity of 3. One final thing you will notice in many of these questions, this might be one of them, it says, what is the minimum degree? And the reason is, if I asked you, what is the degree of this polynomial function, you really could say the degree is 11. You could. You could say that this has a multiplicity of 9. Because it's an odd number greater than 1, it will have that kink to it. And this has a multiplicity here of 2. And when you look at the total degree, it's 11. So we say the minimum degree, and whenever you're seeing the minimum degree, that means if it's tangent, go with degree 2. If it's an inflection point, go with degree 3. All that being said, does anybody have any questions from this section that you would like me to go over or explain? Go ahead, Shazmada. 7? So we have a polynomial function that's given by that equation of the function. I'm going to rewrite it just to highlight for you that there's a factor of -1 out in front. We don't often write it as -1 in brackets. Sometimes you'll just see a negative, but that means there's a factor of -1. And then we have x minus 4 quantity. I'm hoping that that's just an error in what's up here, that it's squared. And then an x plus 3 squared as well. So what this means is if I look at x-intercepts, I have an x-intercept at 4, and there's a multiplicity of 2 with that x-intercept, because the x minus 4 is what produces the x-intercept of 4, and it's x minus 4 squared. That factor occurs twice. I also have an x-intercept of -3, and it also has a multiplicity of 2. So what this means is if we sketch this graph just based on that, we have to have 2 tangent points to the x-axis, one at 4 and one at -3. So there's going to be a tangent point here. I won't abbreviate too much here. And there will be a tangent point at -3. Did I get those numbers right? +4 and -3? Okay. So this will be a tangent point as well. Now the only thing that remains is we have to investigate what's called the end behavior of the function. So answer questions like, are both arms in the same direction or are they in opposite directions? And what is the right arm doing? And the answers to those two questions are found by really looking at the leading term of the polynomial function. Right? We can see, since it's degree 4, the leading term will have x to the 4. But we also want to look at the coefficient of the leading term. And if I expand out this polynomial function, I am going to need to take -1 times x minus 4 times x minus 4 times x plus 3 times x plus 3. I'm going to have to multiply all that out. And I'm not going to multiply it all out. But again, and I feel that as though my explanation on this yesterday was a little weak, so I'll really make it clear today. to get the highest degree term on the polynomial function, you have to multiply the highest degree term of each factor. And the highest degree term of the x plus 3s is x. The highest degree term of the x minus 4s is x. So far we have x times x times x times x. 4 of them. And when we take a look at this factor here, when you take a look at that factor there of -1, it only has one term in it, and the term is -1. So the highest degree term is -1. So all of those yellow underlined bits are going to give us the leading term. Now, again, you're going to get all this filler stuff. You don't really need to look at the constant term, but I want to remind you that the constant term gives you some valuable information as well. If you multiply the constant term in each factor, I'm overlining these things, that -1, as well as being the highest degree term in that factor, is also the constant term in that factor. So the constant term of the polynomial will be -1 times -4 times -4 times 3, which I think is -144. I'm pretty sure about that. So the constant term is -144. We would probably just write -144. And all that means is that the y-intercept is -144. But the most important aspect is this, Shazmaida. The leading term is -1x to the 4, which means it's an even polynomial function because of the even degree, 4, which means both arms are either up or down. But since the leading coefficient is negative, -1 is a negative number, that means that the right arm must be down. But the only way the right arm can be down if both arms are in the same direction is if the left arm is down as well. So when we sketch this thing, since both arms have to be down, we have to start sketching here. I always think left to right. So when I start, I'm starting on the left, but I have to start in quadrant 3 because that arm is pointing downwards, and I have to finish over here. So all that is important here, everybody, is that it looks like this. And I'm a little off base there on my second X-intercept, but I don't care. If I were writing an exam, I would erase that and clean it up a bit. It's going to look something like that. And this is just a double check here. We do have a negative y-intercept. Are you okay with that now? Okay. Any other questions before we get started today? All right, then. We have a lot to do today. Well, a couple of little things to do and then one other addition to what we learned yesterday. So there's really kind of 3 mini lessons, and I would say that the first one is this, and the third one is this, and the stuff in between, well, actually, I'm going to add to this. The first one are these two together. And I feel as though you should be able to answer problems that are applications of y equals x cubed, or y equals x to the 4, or y equals x to the 8, or y equals x to the 11, because they're polynomial functions. But there's a section in your textbook that talks specifically about these functions. When we talk about y equals x to the n, that includes y equals x to the 1, x to the 2, x to the 3, x to the 4, etc. But you know what? You should know what these look like. And we'll review this in a second in that example. What we're going to really focus on today is the middle portion here that I haven't highlighted yet. We're going to focus on this. This is the most important aspect of today. It's going to be almost identical to what we did yesterday with a little added layer to it. And then we're also going to be doing something else which deals with inequalities and polynomials. So to begin with, if I give you f of x equals x cubed, this is example 1, and I say, what's the equation of 1/3 f of negative 2 times x minus 4 and then plus 3, that's really nothing new. But this is almost day 2 of this course, because you need to remember here that the cubed is the f, right? It says f of x is x cubed. So f of hearts is hearts cubed. F of puppy is puppy cubed. F of negative 2 times x minus 4 would be negative 2 times x minus 4 cubed. Do a bit of highlighting here in case you're watching this on video or somebody else is watching this on video later. This part here, including the f, is what I've just written here. I've applied the function f to negative 2 times x minus 4. The rest of it is simply putting in, well, we have 1/3, and then we have plus 3. So this is the equation of the transformed function. That's it. And this goes back to Unit 1, which wasn't that long ago. We're only on Unit 2. It goes back to Unit 1 where we can identify that A is 1/3, B is negative 2, H is 4, and K is 3. And it says describe the transformations. I'm going to describe them in very abbreviated form, which you wouldn't want to do for a written response. We have a vertical stretch by a factor of 1/3. We have a horizontal reflection. And the reason we have a horizontal reflection is because B is negative. We also have a horizontal stretch by a factor of 1/2, because the horizontal stretch factor is always the reciprocal of the absolute value of B. And then we shift it 4 units to the right and 3 units up. And again, all of that would be put into words if you had some kind of a written response. Any questions with example 1? Okay, so you are expected to know in this course what y equals x to the n looks like. Now, I don't include in this little discussion we're having here y equals x to the 1. You know y equals x to the 1 is a straight line going through the origin where y equals x. It's the same line that you reflect functions across to get inverses. I'm talking about you're expected to know what x cubed, x to the 5, x to the 7, x squared, x to the 4, x to the 6 look like. And you'll notice that I've broken this down into odd functions and even functions in terms of polynomials. And I'll show you what they look like in a second, but you should be able to tell me what they look like. For example, if I said to you, sketch the graph of y equals x to the 6, you would say there's an x-intercept of 0, and there's a multiplicity of 6. And 6 is an even multiplicity, so this graph will be tangent to the x-axis at the origin. And since it's an even degree with a positive leading coefficient, both arms are up. So this is a very, I would describe it as almost a very boring graph. It's going to look like this. Roughly, just based on what you know. Both arms have to be up because the leading coefficient is positive and it's an even polynomial. And there's only one x-intercept of 0. My graph is a little off kilter there, but there's only one x-intercept of 0. And it's an even multiplicity, so it has to be tangent. I think it's useful, though, for us to take a look at these. We'll start with even. And I'll just show you what x squared looks like. And you know what x squared looks like, right? So what's the difference now if I go to y equals x to the 4? Well, if I go to y equals x to the 4, it's still tangent at that point, but it goes down more severely to that point. And I know that it looks as though it flattens out and there's a horizontal portion to the graph. There isn't. It just is a lot steeper on the arms and a lot less curvy on the bottom. And if you were to go to y equals x to the 6, you would discover that that severity becomes even greater. I don't think understanding the difference between all of these, and here's x to the 8, is that crucial. But I show it to you because some people go, well, if x to the 6 is tangent at the origin and x squared is tangent at the origin, what's the difference? There is a difference. If I were to go to odd polynomial functions, you should be able to understand why x cubed as a polynomial function you should be able to figure out why x cubed as a polynomial function looks like that. And my axes got turned off. Let me turn them back on. Because x cubed is x times x times x. There's only one factor that's unique. It's x. So the x-intercept is 0, but it has a multiplicity of 3 so that it inflects. There's an inflection point. I suspect that many of you would understand that following the same kind of thing that happened when you go from x squared to x to the 4, the same kind of thing happens here. The severity of the point of inflection becomes greater, just like the severity of the point that was tangent became greater. So, you had no questions about example 1. Does anybody have any questions about what these graphs look like? Go ahead, Ian.
For the odd exponents that makes an S shape, is one half of that S shape the same as one half
Of the even? Kind of, except the exponent is different, right? So the severity of it would be different. What I would say to you, and I don't want to spend a lot of time with this, but the half of the x cubed shape is somewhere between the half of the x squared and the half of the x to the 4. Do you get my drift? Okay. That's what you were asking? Yeah. I just don't want you to think that if you took the absolute value of x cubed, you would get x squared or x to the 4. You would get, I don't know, there's not really an equation for it other than to say the absolute value of x cubed. But it would be somewhere, it would appear somewhere between the shape of x squared and the shape of x to the 4. Any other questions with this? Okay, so now let's get to the meat of this lesson. Example 2, determine the equation of each polynomial function. And if you did sufficient practice with yesterday's work, this is like stealing candy from a baby. Because we look up here and we go, well, there's 3 x-intercepts. We have an x-intercept of -1, which means our polynomial function must contain a factor of x plus 1. We have an x-intercept of 2, which means our polynomial function must contain a factor of x minus 2. We have an x-intercept of 3, and that means that our polynomial function must contain a factor of x minus 3. We can do a little check here. If I were to expand out what I believe is the answer, I would get x cubed as a leading term, which means it's an odd polynomial function. So if I look at the graph, the 2 arms should be in opposite directions. And since if I were to expand this out, I get positive x cubed, the right arm should be up, and it is. As a further check, if I were to multiply the constant term of each polynomial function, so I'll dispense with the color coding now, I would end up with plus 6 as a constant term, and when I look at the polynomial function's graph, it does cross at 6, so we're good. So at number 2b, We're asked to determine the equation of the polynomial function. So again, we're investigating the x-intercepts. And you know, something that was maybe so obvious to me, I made a mistake. It wasn't a mathematical mistake, but it was a teaching mistake. These three factors all had multiplicities of 1, right? Because the graph went through cleanly. To me, it was just obvious. I didn't draw our attention to it, but these all had multiplicities of 1 because each of the x-intercepts are what we were calling clean. No wobble, no wavering, no hesitation. Here, we do have one tangent point, so we have to be careful here. I'm just going to make a very quick chart with x-intercept and multiplicity. We have an x-intercept of -4 with a multiplicity of 1 because it goes through the graph, goes through the x-axis at -4 cleanly. We have an x-intercept of -1 also with a multiplicity of 1. And then we have an x-intercept of 3, but the multiplicity is 2. And again, we always assume the minimum multiplicity. We wouldn't say it's 4 or 6. And that means that based on what we did yesterday, this is what you would do with this. You would say that the polynomial function is x plus 4 to the 1. And you probably wouldn't even write to the 1 unless you want to really draw our attention to it. X plus 1 to the 1 and x minus 3 squared. Except that's not right. And we didn't really have to look at this yesterday too much. The reason it's not right is if we expand this out and investigate the first term and the last term of the expanded polynomial function, they don't match the graph. And I'm going to tell you right now, this is not how you're going to do this. Okay? I'm going to show you one way to do it, but then I'm going to say that this way doesn't always work. If you expand this out, I mean, you can do it this way in this case. You would end up getting x to the 4 plus a whole bunch of filler. And then if you multiply out the constant terms, you would have 4 times 1, which is 4. And then you would have times -3 times -3. -3 times -3 is 9. Sorry, my brain stuttered there for a second. -3 times -3 is 9, times the 4 is 36. And we have a couple of issues here. And again, I'm going to show you how you could do this, but I think for many of you it doesn't even really, it isn't easy to do it this way. What are two issues with what we believe the answer to this question is based on the graph? There's two problems here. Jonathan, what's one of them?
Well, one is both of the ends are pointing down, meaning the leading coefficient would have to be negative.
Right. The leading coefficient of what we believe is the answer, this, which obviously can't be the answer, that has a positive leading coefficient of +1 because it would be positive x to the 4. But we can see that both arms are down, so there's that issue. There's also, and it's really connected, the issue that the y-intercept of what we believe the answer to be is 36, and we can see very clearly not only is it negative instead of positive, it's not even 36. So I'm going to throw this out as a method. There is some number that we could put here that would fix everything. And I don't think this is the best method to do this, to just ask yourself what number it is. But how many of you see the number must be a negative number? There's some numerical factor that must be negative that you would multiply through to change all the signs of the term, so you would get negative x to the 4 and your y-intercept would become negative. And the question becomes then, what number would it be that you multiply by 36 to change it into -40? And I think this is easy for some people and a brain buster for others. How many of you believe you know the number that you would have to have there to change the 36 to negative 40? It's not simple, right? I see one hand going up, maybe two. So you don't want to just look at the y-intercept and answer the question. What you want to do is use algebra. And this is the method you're going to use. From now on, when you make your polynomial function, you don't do that, you do this. You say that there is always going to be a number in front. And I'm not going to do it, but if you did the previous question by putting a number in front and then did what I'm going to show you we need to do, you would get the number being 1. So it was just not necessary here. Okay. So let's take a look at this. I hope many of you know what we call that A in the context of this question. What is it? Does anybody know? Yep. It does happen to be a vertical stretch factor, but in the context of what we're trying to do, we're trying to find it. So we call it a missing parameter. Right? We've talked about this missing parameter thing before. How do you find a missing parameter? You have to put in, so this is a missing parameter. We need to put in to that equation that we have something for x and y. In this case, x and p of x. And we can use the y-intercept. That point is 0, negative 40. So if we put negative 40 in for p of x, which is the y-coordinate, and 0 in for y, 0 in for x, you're going to be able to solve for A. So simplifying this, I have negative 40. It's probably not going to come as a big surprise to you that when you multiply out all of these other numbers, you get 36. You get what we thought the y-intercept was without any correction. So we end up with A times 36, and now we can figure out what A is. This is the only addition to what we did yesterday, is that it's not always going to be A is 1 or A is negative 1. Could be some other number. So what do we get here? We get A equals negative 40 over 36. We can reduce that down by dividing top and bottom by 4 and getting negative 10 over 9, I believe. Is that right? So before I write out the answer, I had asked you before, how many of you can see what you multiply 36 by, which was the wrong y-intercept, to turn it into negative 40? That's the number. So it isn't like it pops into your head. It's a weird number. Bottom line is now we have to take that negative 10/9 and throw it back up in here where we had A. And we will have then P of X or Y. P of X or Y is equal to negative 10/9. X minus 4, nope, X plus 4, X plus 1, X minus 3 quantity squared. So that's the equation of the polynomial function. Let's try another one. So we build this function. I'm going to use y here. I could use f of x because the graph is labeled as f of x. We know there is a parameter here, and incidentally, we don't have to use the letter a. As Ian pointed out, this number a is in fact the parameter a from Unit 1. It's a vertical stretch factor and or a vertical reflection parameter. But sometimes I'll see the letter c out there, or k. It doesn't have to be a. It is going to contain this polynomial function as well, a factor of x plus 1, because we have an x-intercept of negative 1. And that multiplicity is going to be 1 In other words, the exponent or degree on that factor is 1 because the shape of the graph through that x-intercept is clean. On the other hand, we have a factor of x minus 2 because this x-intercept is positive 2. X minus 2 has a 0 of positive 2. And this will be degree 3 because the shape of the function as it passes through that x-intercept is inflected. There's an inflection point. So now we just have to find a. Again, what you can do in this particular case is use the y-intercept. By the way, just look up here for a second. If you didn't put that a there, could you figure out what number it is without using algebra, just using your head? Well, if I expand this polynomial function out, do you see the constant term will be negative 8? Can you figure out what that y-intercept of negative 8 would need to be multiplied by to turn it into negative 24? Yes, 3. Right? But it's not always going to be that simple. Okay, that's why I'm showing you the algebraic approach, which is to put an a here, hang on to your question, Ian, and to load in an ordered pair into the template you've built. So now we're going to get negative 24 equals a times the x-coordinate of that point is 0, so 0 plus 1. I don't know why I keep writing raised to the 1. You don't need to do that. And 0 minus 2 quantity cubed. So we get negative 24 equals a. This is 1. This whole thing is negative 8. So you end up with negative 8 times a equals 24, which is negative. When you divide both sides by negative 8, you get 3. So then you write the polynomial function with that value that you found in for a. So we get for a polynomial function 3 multiplied by x plus 1 multiplied by x minus 2 quantity cubed is equal to p of x or f of x or y or whatever notation we're interested in. Go ahead, Ian.
How do you know that the factor x minus 2 has an exponent of 3?
Because the graph has an inflection point.
Well, how do you know it's not x minus 2 to the exponent of 5?
Because, as I've said before, we always assume the minimum degree.
Oh, okay.
Otherwise, it's an impossible question, right? Always assume the minimum degree. You know, there could be a question that might say to you, multiple choice maybe. I think it's a cheesy kind of question, but given the graph of this, which of the following is not a possible degree for the polynomial? In which case, you know, you could go to higher degrees and still get the proper answer. Bottom line is the degree of this polynomial function in the context of what I'm just making up to explain my answer, it must be even. Because you have a multiplicity of 1 and then you have some other odd multiplicity. But we always assume minimum. Any other questions with C? Okay, I think you guys get the hang of this, but let's just run through a couple more. This would be y equals, I'm going to write out my thoughts, and I want you to take a look at it and just mentally digest it. Some number, I'm going to use k this time just to be different, multiplied by x plus 3, multiplied by x minus 5, quantity squared. I hope that makes sense to everybody. Yes? Oh, I'm missing one, aren't I? X plus 1? And by the way, maybe it's good that I kind of missed this one. Well, it's not good that I missed it, but the order that you write these in doesn't matter. Does that look better now? Okay. I think just by inspection, looking at the graph, we can see that A or K in this case that I've chosen must be negative because the right arm is down. We could just do a check here. Both arms are down on the graph, so the sum of the multiplicities must be an even number, and it is. So now, how do we find K? Well, this is 0, negative 50. So we put negative 50 in for the y coordinate, 0 for the x coordinate. What do we get? Negative 5, quantity squared is 50. 50 times 3 is 150. Sorry, 75. Go ahead. Thank you. What did I say? Wow. The negative 5 squared is 25. Thank you. Times 3 is 75. Times the 1 is still 75. So we end up with negative 50 equals k times 75. We divide both sides by 75 and get negative 50 over 75, which is negative 2/3 in reduced form. Is my reduction correct? I'm pretty sure it is. But I also said a second ago that negative 5 quantity squared was 50. So what does that mean? It means our polynomial function is y equals p of x equals f of x, whatever notation is appropriate, negative 2/3, and then multiplied by all of our factors. This is definitely a case, everybody, where you could have said that if k was 1, the y-intercept would be 75. And I think many of you would figure out that you need to multiply 75 by 2/3 to make it 50 and a negative to turn it around. But again, it's not always that simple. And as the next example, which I believe is the last one in this section, is going to illustrate, sometimes you don't even know the y-intercept, so you can't do it with that kind of investigative approach of looking at the y-intercept and saying, what do I do? So we build our function. I'll go to p of x this time. P of x is equal to some constant. I'm going to use c this time, just illustrating that the letter you use doesn't matter. And what do I have? I have an x plus 3. I have an x minus 1. And I have an x minus 3 quantity squared. So there's only 3 x-intercepts, one at negative 3, which gives me a factor of x plus 3. That's really the factor theorem. One at positive 1, so it gives me a factor of x minus 1. And one at 3, positive 3, so it gives me x minus 3. But we can see it's tangent at 3, so the minimum multiplicity that we would assume is 2. This time you don't have a y-intercept to work with, but you do have the coordinates of another ordered pair or point on the curve. We can use that. This says that when you put in 2 for x, you have to get 15 for y. That's what a point on a graph of a function means. It means when you use that x-coordinate, you have to get that y-coordinate coming out as an output. We simplify this. This is 5, this is 1, this is 1 as well. 2 minus 3 is negative 1. When you square negative 1, it becomes positive 1. So we end up with c equals 3. You have to take 15 and divide by 5 to get c. So the polynomial function is p of x equals 3 times x plus 3 times x minus 1 times x minus 3 squared. Now, just a quick note before we go to the very final layer of this math sandwich today, the bottom slice of bread. This forgetting about A is an exam killer for some people. You know how in the first unit exam you might be given f of 3x minus 12, and you need to remember to factor that 3 out to make sense of the horizontal translation. And you remember how I told you that there could be like 3 or 4 multiple choice questions and potentially a written response question where that becomes significant, which means you could just, your mark could tank. Your mark could change by 20% by forgetting that one thing. This is the equivalent here. Forgetting to consider that there might be some constant multiple you're multiplying all the factors by can really hurt you on an exam, especially if there's a written response that I give you a graph and ask you to find the equation for. This is the thing you want to really pay attention to. So any questions with that final example? All right, so we have one more thing to do. Question 3 says, determine the intervals where this polynomial is positive and where this polynomial is negative. So what we're really asked to do here, well, I'll say this first. When you see at this level what is an interval, we're talking about x. Okay, we're talking about an interval xy's. But the problem is, when we say where is this positive and where is this negative, this thing is thought of as y equals negative 1 times x plus 3 times x minus 2 cubed times x plus 2. When I say where is that positive, I'm saying where is y positive. And this was something you did with quadratics in Math 20-1. It's really simple when it's explained to you, and then you start thinking about it on your own. You kind of go, what am I doing here? So what we're doing is we're finding out where y is positive, but we're going to answer it in terms of what the values of x are that give those positive values of y. So another way to look at it is what we're doing is you're solving this inequality. You're telling me where this thing is greater than 0. But keep in mind, again, this whole thing is y. We're also solving this inequality. Where is it negative? And again, keep in mind this whole thing is y. For those of you in my calculus class, we will be solving inequalities in a totally different way that will make more sense in calculus class than what we're going to do here. All you're doing here is looking at the graph. That's all. And we can use a graphing calculator, or we can use our knowledge of multiplicity and everything else that we've learned about factors and zeros. For example, this graph will have an x-intercept of negative 3. It will have an x-intercept of negative 2. And it will have an x-intercept of positive 2. And the x-intercept at negative 2 will be an inflection point. Because the x-intercept at positive 2 will be an inflection point. So this will be an inflection point here, and the other two will be clean. If I were to expand this out, I hope everybody sees that I would get negative x to the 5. Because I'm going to have x times x times x times x times x, which is x to the 5 times the negative 1, which means it's an odd polynomial function. The right arm is down because it's negative x to the 5. The graph will start here and end here. The only way to do that is to do the following: through, up, and through with an inflection point. This is what the polynomial function looks like. I mean, roughly. So take a look at this inequality, which is talking about where the polynomial function is positive. The polynomial function is positive here, here, here. In those two regions, the graph is positive because y is positive, it's above the x-axis. So in terms of that, and I'm not asking you to color code things, this is just for my teaching purposes. This is a region where the polynomial function is positive. This is a region where the polynomial function is positive. And I'm presenting it that way because we have to answer it by talking about x. The polynomial function is positive whenever x is less than -3 and whenever x is between -2 and 2. We do not include the equals to in the inequalities that we write. So I'm going to add something to what you're looking at that's wrong. I'm going to go back in a bit and get rid of it. But if you said the following, and you decided to say, I'm going to include those points, that would be wrong because the polynomial function is not positive at those points. The polynomial function is 0 at those points. So we would not include the equals to here. I'm going to finish this off by now talking about where the polynomial is negative. The polynomial is negative. Well, it's negative here in this region, and it's negative in this region. So it's negative in this interval, and it's negative in that interval. And again, I don't know that you reproducing everything that I'm writing on the board on your notes is going to be helpful later. This is just for in the moment kind of learning. So the polynomial is function is negative between -3 and -2, and when x is greater than 2. Ian, go ahead.
How come we don't use the unison sign that we did last?
The what?
The unison sign?
Unison.
Yeah. The U, when we're writing
Union.
union.
You could. There are other ways. There are many ways that you could write this. Generally speaking, the union symbol is done if you did it this way. I mean, you have to be adaptable. There's lots of different languages we can use here to describe what amounts to domains here. These are domains of X that produce positive or negative. Any questions with that first one? All right, let's take a look at this one. Sometimes it's okay to be lazy. Well, lazy is not an admirable quality, don't get me wrong, but sometimes you're writing an exam and it might be a multiple choice question. If it said, where is f of x greater than 0, and it were multiple choice, I would be inclined to take a look at the graph of the polynomial function. I know I can look at those zeros and multiplicities, zeros based on the factors, and get that, but sometimes a person just needs a break. X minus 3, we have an x plus 1, and that is raised to the power, the exponent of 2, and we have an x minus 2. Just make sure I got all that right. X minus 3, x plus 1 squared, x minus 2. I'm going to go zoom 6. I know what the x-intercepts are going to be. So looking at that, I know that the graph at -1 is tangent, which, you know what, I mean, I could have just looked up here, right? But it takes the thinking out of where the arms go. It goes through 2, and it also goes through 3. This is 3, this is 2, this is -1. So where is f of x positive? It's positive in this region. It's also positive, not here, but it's also positive here. These are all places where it's 0, and it's also positive here. There's 3 intervals that this is positive in. I'll use the interval notation here. X is an element of -infinity to -1 in union with -1 to 2 in union with 3 to infinity. And by the way, those first 2 sets, -infinity to -1 and -1 to 2, you can't put them together and just say -infinity to 2. And I hope the reason's obvious, but in case it isn't, if you put them together, you're including the number -1, and the polynomial is not positive at -1. Where is f of x negative? Well, it's negative everywhere else. Well, not everywhere else. Everywhere else except for the x-intercept. So it's negative in here. That's it. That's the only place where the graph is below the x-axis, which means it's the only place where y is negative or f of x is negative. So from 2 to 3 using that interval notation. So as I said, we got a math sandwich today. The first layer of bread, or the first slice of bread, was talking about x squared, x cubed, x to the 4, x to the 5. The final layer of bread was solving really polynomial inequalities. That's what you're doing. And I guess technically, I could give you a polynomial in expanded form and ask you on a written response. I wouldn't, but I could ask you on a written response to solve that inequality. You would have to use the factor theorem to factor this so that you could build a graph so that you could answer the question. And then all the pastrami and everything else, everything inside of the sandwich was all this. And the main lesson here is don't forget about that constant multiple out in front. You can see there's practice problems here. Page 149, number 10 is an important one. That's going to be solving the inequalities. And then everything else is in your handout on whatever pages those are. Problems 1 to 18. You know that you don't have to do every single question, but you have to know how to do every single question. So get a good sampling of them. Give me a minute or so to take my attendance and take care of something, and then I'll be around to help you out.